Welcome back to the deep dive. So, we're doing something a little different today.
A little bit.
Yeah, usually we take a huge topic and try to narrow it down, but today we're starting with something that, it literally holds the entire modern world together. Yet most people, they just treat it like it's magic.
Or like a headache.
Right. We're talking about networking, and I know the minute you say networking, a lot of people's eyes just glaze over. They picture, a mess of blue cables
Or
or
some guy in a hoodie typing furiously into a black screen. It feels really intimidating.
it does.
And that's a shame because at its core, networking isn't magic.
Yeah.
Not at all. It's plumbing. It's just pipes and valves for data.
Exactly. And the source material we're working with today is just perfect for this. It's a guide designed for future DevOps engineers. It's called the DevOps Engineer's Guide to Essential Networking Basics.
And I really like that it specifies DevOps engineer.
Yeah.
Because we're not just talking about how to plug in a router at home.
Hmm.
We're looking at how you build the actual infrastructure that
Yep.
keeps a company like Netflix or, Google running. The whole premise of the guide is simple. Stop just memorizing acronyms.
And start understanding the conversation.
Yes, the conversation between devices.
That's the key word, isn't it? Conversation. The guide argues the entire internet is just a series of very, very specific and polite conversations between machines.
Well, ideally polite. Sometimes they shout at each other.
Fair enough.
But yes, the goal of this deep dive is to take you from, I hope the Wi-Fi works, to actually understanding the mechanics. How a request gets from your laptop to a server in Virginia and back, and more importantly, what to do when that journey fails.
So let's start at the very beginning. If we're looking at this as a conversation, the first thing you need is a way to identify who you're even talking to. You can't send a letter without an address.
Which brings us right to the IP address, Internet Protocol.
And most people have seen one of these. It's that string of four numbers with dots in between, 192.168.something.something.
Right. The guide calls it the home address of the computer.
It is, but let's complicate that immediately because that analogy is a little simplistic in a real DevOps context.
It is, yes, it's an address. But we have a crisis with these addresses. The version you just described, IPv4, was invented when the internet was like a tiny experiment. It
Yeah.
allows for about 4.3 billion addresses.
Which sounds like a lot.
It did then.
Until you realize everyone has a phone, a laptop, a watch, and now your smart toaster needs its own IP address.
Exactly. We literally ran out. We are out of them. That's why you'll hear about IPv6.
The new one.
Yeah, this incredibly long, complex string of letters and numbers. It was made to solve the shortage. But, and the guide makes a really good point here, even though IPv6 is the future, in the trenches of DevOps, you are still going to be wrestling with IPv4 every single day.
So we're stuck with the old system for a while.
Yep.
Okay, but here's the concept that I think trips a lot of people up, and the guide spends a lot of time on it. The difference between a public IP and a private IP.
This is probably the most important concept for security. Hands down. Think of it this way. Your public IP is the street address of your whole apartment building.
Okay.
Anyone in the world can see it, drive by it, send mail to that building. It's how the internet finds you.
But I don't live in the lobby of the building. I live in apartment 4B.
Right. And apartment 4B, that's your private IP. It's your 192.168.1.5 inside your house. The crucial thing here is that the outside world, Google, Amazon, hackers,
Yeah.
they cannot see apartment 4B.
They only see the building.
They only see the building. So your laptop has this private address that only your home router knows about,
And that's on purpose.
completely by design. If every single device had a public IP, just directly exposed to the internet, security would be an absolute nightmare. You don't want the whole world to be able to ping your smart fridge directly.
No, you definitely don't.
You want them to have to go through the front door, the router first.
Okay, so we've got the building address, the IP, and the apartment number.
Wait.
We don't have the apartment number yet.
Not yet.
My computer's doing more than one thing at a time. I might be streaming music, browsing the web, checking my email, all on one machine. How does the data know which application to go to?
And that is where ports come in. If the IP is the address, the port is the specific service window or door you're trying to reach.
The guide lists a few celebrity ports that it says we should all know.
There are thousands of them, but yeah, a DevOps engineer really only cares about a handful. Port 80 is the classic. That's HTTP.
Standard web traffic.
Standard unencrypted web traffic. If you spin up a web server, it listens on port 80 by default.
But we don't really use port 80 that much anymore, do we? I mean, everything just redirects to the secure version.
We do, but you still need to know it because you have to set up that redirect. The secure version is port 443. That's HTTPS. If you're building a secure application, you are living and breathing port 443.
And what about actually managing the server? If I'm an engineer and I need to log into a cloud server to fix something, I'm not using a web browser.
No, you're probably using SSH Secure Shell, and that lives on port 22. This one is huge for security.
How so?
If you were to scan the internet right now, you would find millions, literally millions of bots just knocking on random IP addresses at port 22 trying to guess passwords.
That is a terrifying thought. So practically, if I leave port 22 open to the entire world in my firewall settings,
You are asking for trouble. You are essentially leaving the back door of the bank unlocked. A good engineer locks port 22 down so it only accepts connections from, say, their specific office IP address or a secure VPN.
okay, so we have an address, the IP, and a specific door, the port. Now we need to talk about how the data actually gets delivered. The guide gets into protocols here. TCP versus UDP. To me, this always felt like slow and steady versus fast and loose.
That's a pretty fair way to put it. Let's look at why you need both. TCP Transmission Control Protocol is the micromanager of networking. It is obsessed with reliability.
The guide uses the registered mail analogy.
It fits perfectly. When you send data with TCP, your computer sends one packet, and then it literally waits for the server to reply, okay, I got it.
So it's a constant check-in.
A constant check-in. Then it sends the next one. If a packet gets lost somewhere, the server says, hey, I missed packet number 5, and your computer just resends it.
So guarantees the data is perfect. That's why when I load a web page, the text isn't all scrambled.
Exactly. Or when you download a file, you don't have missing numbers. It's all about accuracy over speed. But all that back and forth confirmation, that takes time. It introduces latency.
And that's where UDP comes in.
User Datagram Protocol.
Yeah.
UDP is, well, it's the honey badger of protocols. It just doesn't care.
It just sends the data.
It just blasts data at the target as fast as possible. It doesn't check if it arrived, doesn't wait for a receipt. It just goes.
Which sounds awful for a spreadsheet, but I'm guessing that's what we're using for things like this call right now.
Precisely. Voice and video. If we're using TCP for this call, and a little packet of my audio got lost, the whole conversation would pause.
It would stop.
It would stop while my computer asked yours to resend that one tiny millisecond of sound. It would be incredibly choppy and awkward.
But with UDP, if a packet drops, you might hear a little glitch. But the conversation just keeps going.
It keeps moving. So yeah, TCP for when it absolutely has to be right. UDP for when it just has to be fast.
You've got the toolkit. Okay, let's see it in action. The guide walks through the life cycle of a request. This is the classic interview question, right? What happens when you type google.com into your browser and press enter?
It is. It feels instant, but there are actually 4 or 5 distinct things happening in those few milliseconds.
Okay, where does it start?
It starts with the name. Your computer has no idea where google.com is. Computers only speak in numbers, in IPs. So step 1 is the DNS lookup, the domain name system.
The phone book of the internet.
It's the phone book, yeah, but it's a huge distributed phone book. Your computer asks a DNS server, hey, what's the IP for google.com? And if that server doesn't know, it asks another one up the chain until it gets an answer. 142.250.something.something.
And this is why sometimes when the internet just feels broken, but your Wi-Fi signal is strong, it's often DNS.
It's always DNS is a common and often true joke in the industry.
You have the road, but you lost the map.
You've lost the map, exactly. So once you have that IP, step 2 is the handshake. Your computer reaches out to that IP on port 443 using TCP. It basically says, hello, I would like to speak, and I'd like to do it securely.
And because it's HTTPS, on 443, there's a kind of secret code exchange that happens.
That's the TLS encryption, transport layer security. They agree on a secret key so that nobody in the middle, not your internet provider, not a hacker in the coffee shop, can read the data. And only once that secure tunnel is built does the server actually send the web page back.
Wow. It really is a massive negotiation happening in the blink of an eye.
It is. Now let's level this up. We've been talking about single computers, but the guide shifts here to DevOps scale. This is where we stop talking about home routers and start talking about cloud infrastructure, AWS, Azure, Google Cloud.
And this is where that term VPC comes in, virtual private cloud.
Right. Think of a VPC as your own private island in the cloud. When a company like, say, Spotify goes to the cloud, They don't just dump their servers into a big public pool.
No.
They carve out their own slice of the network that is logically isolated from everyone else. It's their data center. It's just virtual.
And inside that island, you have subnets. The guide really emphasizes the difference between public and private subnets. Why does that matter so much?
This is a huge architectural decision that it can destroy a company if you get it wrong. A public subnet has a direct route out to the internet. This is where you put things that need to be seen.
Like your main website.
Like your load balancer or your public-facing web servers.
Yes, and the private subnet.
That is a vault. Has no direct route to the internet at all. This is where you put your database, your customer data.
So if I'm building an app, I should never just put my database in the public subnet because it seems easier.
Absolutely not. If you put a database in a public subnet, you are 1 weak password away from a global data breach. You hide it. You put it in the private subnet, and the web server in the public subnet talks to it. But the outside world can never, ever touch that database directly.
Wait a second. But if the database is in a vault with no internet access, how does it download security updates? It needs to reach out to the internet for that, right?
That's the paradox.
Yeah.
And the solution is a very clever thing called a NAT gateway, network address translation.
The guide used another analogy for this one, the receptionist.
It's a good one. Imagine the database wants to download a security patch. It can't go to the internet itself. So it hands the request to the NAT gateway, the receptionist.
And the receptionist is in the public area.
Exactly. The NAT gateway sits in the public subnet. It takes the request, goes out to the internet, gets the file, and then hands it back to the database.
So the database can start a conversation going out, but nobody on the internet can start a conversation coming in.
Precisely. It's one-way traffic, purely for safety.
That brings us to the bouncers of this whole club, the firewalls. In the cloud, these are often called security groups or network ACLs.
This is your first line of defense. A security group is just a list of rules. And by default, good security practice says deny all.
So nobody gets in.
Nobody gets in unless I specifically put their name on the guest list. So you have to explicitly say, allow traffic on port 443 from anywhere in the world.
Right. And allow traffic on port 22 only from the Office VPN.
You got it. A lot of major outages happen because someone just forgot to update the guest list.
Okay, and finally, for the really big websites, we have the load balancer.
Right. If you're running a site like Amazon, you don't have one server, you have thousands. The load balancer sits at the very front door. When a request comes in, its only job is to decide which server is least busy and send the traffic there. It's the traffic cop.
And it also handles failure, doesn't it, if server A blows up?
The load balancer sees it instantly and just stops sending people there. It reroutes everyone to the healthy servers.
So it provides redundancy. To the user, the site never even went down.
Exactly. Even if half the servers behind the scenes are, on fire.
Speaking of things being on fire, let's get to my favorite part of the guide, the DevOps toolkit. Because, inevitably, despite all of this perfect planning, the site will go down.
It is not a matter of if, it is a matter of when.
So let's play this out. It's 3:0 a.m., your pager goes off, the alert just says, production is down, you open your laptop, the guide lists 5 tools, ping, curl, nslookup, traceroute, and netstat. How do you actually use these to solve the crime?
Okay, detective mode. First thing I do, I need to verify, is the server even there? I use ping.
So you type ping and the server's IP address.
Right, it sends a tiny little packet. If I get a reply, I know the server's on and the network path between us is clear. If I don't get a reply, a timeout, then I know I have a connectivity problem. Maybe the server crashed, maybe a firewall is blocking me.
Okay, let's say ping works. The server is alive. But the website still won't load in a browser.
Okay, now I check the application itself. I use curl. I type curl-i and the website URL. This acts like a browser, but just gives me the raw text-based headers. I want to see if the web server sends back a 200 OK, which is good, or a 500 internal server error, which is bad.
What if curl just hangs forever? It doesn't give you anything back.
That usually means a firewall is just dropping the packet silently, or the actual web service like Nginx or Apache has completely frozen.
Okay, new scenario. You try to ping google.com and it fails, but then you ping 8.8.8.8, which is Google's IP, and that works.
Classic. That is a DNS issue, 100%. You can talk to the IP, but your computer can't figure out what IP google.com is. So then I'd use nslookup to start digging into the DNS records.
What about when everything is just crawling? The site works, but it takes 30 seconds to load a page.
Then I'm breaking out traceroute. This tool literally maps every single jump your data takes across the internet. from your laptop to the server. It might show me that traffic is getting stuck at some random router in Kansas. It helps prove it's not my server, it's the internet in between.
And finally, Netstat.
That's an internal tool. If I can get onto the server itself, I run Netstat to see who is connected to it. And maybe I see 10,000 connections all from a single IP address in Russia.
Oops. You're under a DDoS attack.
Exactly. Netstat shows you the active battlefield on the server itself.
The guide wraps all this up with what it calls the troubleshooting mindset, which basically says, don't panic, be logical.
Which is easy to say, but hard to do when the company's losing money every second things are down. But the checklist they provide is just solid gold.
Go through it.
1. Is it DNS? Can I resolve the name? 2. Is it the network? Can I ping the IP? 3. Is it a port or firewall? Is the door locked when it should be open? And 4. Is it the application? Is the service itself actually running on the machine?
It's a process of elimination. You start from the outside and you work your way in.
And that really is what DevOps is all about. It's not just writing code. It's understanding the whole environment that your code lives in. You can write the most brilliant application in the world, but if you put it in a private subnet with no NAT gateway and a firewall blocking port 443, it's completely useless.
It's like building a Ferrari and then parking it in a garage with no door.
That's a perfect visual, yes.
So for everyone listening, whether you're an aspiring engineer or just someone who wants to know why their Netflix is buffering, remember that networking isn't magic.
Not at all.
It's just a series of logical rules, addresses, and permissions.
It's this complex, invisible negotiation happening millions of times a day. And honestly, once you understand the plumbing, you start to really appreciate just how amazing it is that it works at all.
Absolutely. Next time you click a link and a page loads in under a second, maybe give a little mental nod to the DNS server, the TCP handshake, and the load balancer that made it all happen.
They're the unsung heroes of the internet.
Thanks for breaking down all the plumbing with us today.
Always fun to look under the hood.
We'll catch you on the next deep dive.